Let's get started. So we're talking about making the web functional with Phoenix and Elm. These are different tools and technologies, right? But we're actually seeing a lot of cross-pollination between these two communities, a shocking amount, actually. So I was just at another conference last week, and we had it was an Elixir conference, and we had two talks that incorporated Elm in some way. And the same thing happened at ElixirConf last year. So I'm really excited to see where we can kind of bridge the gap between Phoenix and Elm. And we have some exciting things in the pipeline that I think the community is really going to love. I think Evan can tell you about the Elm side of things. But first, we're going to talk about what makes the web dysfunctional today on the server. So obviously, I don't have to tell everyone here, like, there's no more free lunch, right? You don't have clock speeds bumping. Our programs aren't getting faster every year. We're having the multi-core age is kind of changing the game. And at the same time, we have the world moving from mostly stateless request-response style architectures to increasingly stateful ones. And this is kind of really the game changer. It's what brought me into the Erlang ecosystem and ultimately got me into creating Phoenix. I think the stateful architecture is really at odds with most languages' concurrency models or a lack of concurrency models. So you used to have easy horizontal scalability where you could just have a request come in, read some state from a database, fulfill that request, and throw that state away. But now that we have stateful connections, we have ongoing conversation. Vertical scalability becomes really, really important. And I think most languages that have heavy concurrency models are really falling over in this area. And I come from a Ruby background, and any kind of object-oriented solution to try to handle a stateful conversation with the server was incredibly complex and kind of pushed me over to the functional side of things and ultimately to Elixir and Phoenix. We also have kind of this functional web on the client. I think no one would argue that JavaScript is solving everything extremely well. We have a lot of good tooling in JavaScript, but we have a lot of fragile tooling. The biggest source of new issues on the Phoenix issue tracker are JavaScript related. And I did not think I'd spend a huge amount of my time debugging JavaScript when I created an Elixir web framework. And we integrate with a existing build tool, and we don't even couple with it, but just having it shipped by default with Phoenix has issues with people having repeatable builds. The Node ecosystem follows Simver, but everything breaks when new packages are released. So we're seeing a lot of fragile tooling. And we have a lot of competing async models on the client. So whether it's like continuation style callbacks or promises are really hot now, or your competing implementation of promises, you just have all these competing models to accomplish different things. And this is leading, I think, in large part to the framework churn, the framework fatigue that we have. And I think the JavaScript community is trying to seek ideal architectures for the applications, and they haven't quite found it yet. So we have a new framework that tries to come in and solve it, but ultimately we're dealing kind of with I think, inferior language. And I think my hope is Elm comes in and fills this gap. And for me personally, is going to be my kind of ejection out of the JavaScript community into something far greater. And we'll hear all about that from Evan in a little while. But I'd like to talk a lot about the Phoenix milestones that we hit over the last 6 months. We released the Programming Phoenix book. Actually just finished it, so it should be out in print, I think probably within about a month. It's available as ebook now. I wrote that with Bruce Tate and Jose Belin. It was a lot of work, but I'm really happy with how it came out, so check that out. I'm really excited about how that's going to fuel the adoption of Elixir and Phoenix in general, is having kind of first-class education resources available. And then I also, the big part of Phoenix development over the last 6 months is Dockyard's support of the project. So I hopped on at Dockyard about 3 or 4 months ago, and since then I've been working almost entirely full-time on Phoenix. So Dockyard hired me for my actual role is to spend the majority of my time on open source development. So that's been what I needed to have kind of a sane life trying to manage a large open source project, and Dockyard has made a big bet on the framework, so check them out and give them a big thank you. But the biggest story out of the last few months is our PubSub and channel optimizations. We were able to get 2 million channel clients on a single server, which is something that I didn't think we'd ever be able to achieve. This is like, you hear what the WhatsApp scale of 2 million clients per server is what brought me into the Erlang ecosystem. And the fact that we were able to kind of recreate that. I mean, it's not the same. They're doing a lot more than just handling mostly idle connections, but still it's something that's been extremely exciting. And these aren't just idle WebSocket connections. They are actually channel clients multiplexed on a single WebSocket connection as active PubSub subscribers. So there's quite a bit going on behind the scenes other than just raw Cowboy WebSocket connections. And if you ever tried to benchmark or load test anything built on Erlang or Elixir, you'll know that it's actually incredibly hard. So this was a couple weeks of full-time work just to orchestrate to start testing this. It took about, we had to provision 45 Rackspace instances running the Sun load test client. So we had this like fleet of Sun clients opening about 60,000 WebSocket connections each to a single Phoenix server. So just setting all this up was a lot of work. And we had a pretty beefy server. So the server that served those 2 million users it was a 44, 128 gigabyte instance, which is pretty beefy, but it was only about $1,300 a month on Rackspace. So if you're able to support 2 million active users for $1,300 a month, I'm really excited about kind of what barriers that's going to break down. I think it's going to really blow out some use cases that were previously unreachable, especially by the average developer. And this used about 83 gigabytes of memory, so it wasn't, used quite a bit of memory, but you have to remember we had not only raw WebSocket connections, but we also had PubSub system built on top of that, and we also multiplex individual channel processes on top of that connection. So there's quite a bit going on, and we didn't even max this machine. And we were only capped at 2 million clients because I set the U limit at 2 million file descriptors on the server as some crazy high number that we'd never hit, and we ended up actually hitting that. And I didn't have time to go back and rerun the results. Because when you're paying for 50 servers by the minute, these things add up. But one of the funnest parts of this is broadcasting to 2 million subscribers actually works. We load tested this simple chat application. That's horrible. We load tested this simple, all right, I'll just shout. All right. So we had a chat application, and we wanted to stress our PubSub system. So you would never want 2 million users to join one chat app, but we didn't think, once we had these 2 million users set up, we were like, hey, let's go try to use the app, thinking it would just like kill the server. And this is an actual video I took. When I hit enter on the left-hand side, when it reaches both browsers, it's gone out to 2 million active connections, which blew us away. This was like Jose was on Skype with me, and we were like, I think Jose's response was like, Erlang, period. Like, we're just, like, to give you an idea, like, what's happening here is this sends a message to the server, which broadcasts to 2 million subscribers, and like that has to send 2 million messages to 2 million PIDs, and then has to serialize that to JSON for each PID, and then push that down the wire. And that happened in like 2 seconds. So I'm still blown away by it. But I want to talk a lot about the optimization story, because I think telling this story is extremely fulfilling for me, because you come into a new ecosystem or framework and you buy into the hype, you drink the Kool-Aid. I think it's unavoidable, and there's nothing wrong with it. Kool-Aid is delicious, but I think we often have mantras that we spout, like functional programming leads to more maintainable code, the Erlang VM is super scalable, Phoenix is super productive and fast without sacrificing performance. Like, we preach these things, but to have the hype live up to reality for me is like incredibly fulfilling. So I want to tell a story of how we optimize this. Because initially, to get Phoenix 1.0 out, at least the channel layer, it was a whole like make it work, then make it fast. So we had a stable API, and we like, okay, we're following OTP principles, it should be scalable, and we released 1.0, and then we went to optimize. So our first benchmark run only had 30,000 clients before the server was maxed, which is way too low. And I started like having like crushing self-doubt, like what? Like, is this scalable? But we had a quick doubling of performance by removing code, so this was encouraging. So we doubled performance by adding 14 lines of code and removing 69. So it was like, okay, it's like that's pretty good. We simplified the code and got double performance. And then I fired up Observer and found a bottleneck like almost immediately. And that, again, allowed us to have a simplified code base, so add 5 lines of code, remove 38, and we increased our performance by an order of magnitude of where we started. So at this point, I'm feeling like really good. Like, okay, like this is trivial changes. The code is just minor tweaks. Is actually removed code, and we're at hundreds of thousands of connections. And then I thought, okay, like this must be the low-hanging fruit is gone. I'm going to have to like refactor all this code to get those millions of special sauce scale But it turns out our biggest performance improvement was a single line of code change, which increased our arrival rate by 10 times, so the number of connections per second we could open at a time, and it also added 100,000 subscribers. And we were only limited at 450,000 connections because we started with a smaller Rackspace instance. So these optimizations, these diffs you see here is what went from a system of supporting 30,000 subscribers to a system supporting 2 million by actually removing code. And I'm still blown away by this process because we didn't have to do any complex profiling. Like I didn't have to actually run any profiling on this. I just used Observer to make minor code changes and find bottlenecks. So for the second optimization you saw, I fired up Observer, remote Observer shell running on the server during an active benchmark. And I noticed the timer server had hundreds of messages in its mailbox. And I said, like, what the heck, why is the timer server here? And immediately I realized I actually incorrectly used timer send interval, where I should have used process send after or Erlang start timer. And timer send interval is going to use a central timer server to send you a message periodically. So we were bottlenecking the timer server when we didn't even need to. So, but just by removing that, we were able to increase performance 5-fold. And this is how we optimized. We examined our S tables, we monitored message queue sizes, and that's all we had to do to optimize something from 30,000 connections to 2 million. I'm blown away by it. I wouldn't have to dip down into Beam files or running profile tasks. It was almost too easy. And in fact, Adam Kilson, who's here today, I was putting my slide deck together and I saw this tweet, so I had to add it. He said he was playing around with Observer, and it took him 30 seconds to see that he was leaking monitor refs. So I saw this tweet and I was like, oh, this is perfect for right here in my slide deck. And little did I know he was trolling me because 5 minutes after I added it to my slide deck, a memory leak issue was raised on Phoenix PubSub by Adam. So he was actually diagnosing a Phoenix issue that I still have to fix. So he's trolling me. But it turns out, so this should affect very few people, but the moral of the story is someone that didn't write Phoenix or have experience with Phoenix's code base was able to, within 30 seconds, identify an issue and find the exact place in the code that was causing it. And to me, that's such a testament to the tooling that we have available. So it's really cool, other than me having to fix this. And then the 10x increase in arrival rate is pretty cool. So like know your ETS table types. What happened was we were using a bag table for subscriptions, and we changed it to a duplicate bag. And this is what increased our active connections tenfold. Because the bag insert time grows linear in time, and a duplicate bag allows duplicate keys, which lets your insertion time be constant. So since every subscriber is unique, we were able to use a duplicate bag, and this is what gave us a 10x increase in our arrival rate, which is pretty incredible. But that was kind of the top end of our optimizations. We were able to support 2 million users, but we did see at that point we were getting some subscriber timeouts. Sometimes those Sun clients, one of them would run out of memory and crash. And that would drop 60,000 connections at once, which would flood our single local server and lead to timeouts on new subscribers. And then we also noticed broadcasting to 1 million users took a couple seconds, but broadcasting to 2 million was taking like 5 to 8 seconds, which we were thinking, like, wouldn't it be great to condense that back down to a couple seconds? So we realized we could shard our subscriptions, and we would accomplish both pooling of PubSub servers and also parallelized broadcasts. So like anytime you have timeouts to a single server, the solution is pooling, right? So we were able to do both by going from something like this, where each node ran a single PubSub local server, to something like this, where we sharded our ETS tables, which holds our subscribers. A local server managed each ETS shard, and we still use PG2 to broker multi-node connections. And doing this was like remarkably simple. It was like 150 lines of code. And you might be thinking, like, what did we shard by? Like, we don't have users necessarily, but we do have a unique PID, right? So this is the code lifted out of Phoenix where we can just convert our PID to binary, look up on the Erlang docs the binary representation for a PID, and we can pluck out the process ID. So if you want, for example, if we have this PID and we want that number 57, we can just pattern match out that value. And then to pick the shard, you just divide by your shard size, take the remainder, and that's the shard to pick. So every PID knew which PubSub local server to ask to subscribe to, and every PID knew which ETS table to write to. So this was what let us prevent all those timeouts at the top end of our 2 million subscribers, and we also were able to spawn a task then. So when you broadcast, we read from ETS in parallel and broadcast to those users in parallel. So this is what kept our broadcast down to 2 seconds to a couple million users. So that's our PubSub optimization story. So we went from something that supported 30,000 users, which is not great, but it was initial best effort approach. And then with minimal code changes, by actually simplifying code, we ended up with like a world-class solution. And then from there, I've been focusing on Phoenix Presence, which I talked about last year at ElixirConf. And this is really exciting to me because we're putting cutting-edge CS research into practice, I like to say. We're applying some really interesting CS ideas into something that users can use day to day, but not have to actually worry about it. So ultimately, presence is like, the easiest example is like who's online right now in your application. And it seems really simple. It's like deceptively simple. Most people think like, why do you need cutting-edge CS research to show users online? If we have 2 users and 2 browser tabs, we just show them, right? But let's walk through this problem. So initially, most users in the community will implement this. They'll say, I know how to do this. I'll start a presence server that just monitors channel processes, and we broadcast events as they join and leave. And they'll write code that looks like this. I've seen code just like this. Well, they'll have in their channel join, they'll have a presence add, which is going to be like a gen server call. That's just going to set up a monitor and broadcast a user as joined. And they store that state locally. And then anytime they get it down, they're going to broadcast that user as left, and then they delete them from their state. Problem solved, right? Let's walk through this. So there's a few problems with this. One is if we have a user open 3 browser tabs, what's going to happen here? We're going to end up with duplicate users. So at this point, you can have like the client dedupe, but what happens if user 1 closes that browser tab? The server is going to broadcast a leave, and we're going to remove them from the online list, but they're still there. So a user hasn't left until all their presences have left. So there's an extra layer here where you have unique presences for the same user. So there's an issue. But even worse is a lot of newcomers into both Erlang and Elixir will develop an application on their laptop, and they'll just like put state in a gen server and be like, aha, I can deploy this out. But the problem is, as soon as we deploy this multi-node, right, we have a data synchronization problem. If we list our gen server state, it's going to be different between nodes. So there's a synchronization problem that we have to solve. And at this point, most languages or libraries and frameworks will say, aha, I know how to handle data synchronization between 2 computers. We can just put it in a database. We'll just deploy Redis, and we'll have a problem solved. And I don't want to crap on Redis because I've used it many times in the past. I think it's really neat. But I think what happens is when you have a language that doesn't have a good distribution story, it pushes you towards bad solutions. And especially with presence, like presence is all ephemeral state, right? Because either the user's there or they're gone, and when they're gone, that state's gone. So we have, there's no reason to put ephemeral state in some storage engine, right? We have a place to do that, and it's in processes. But let's walk through this. So the best case scenario is where most people end up is something like this, where their presence server is going to read and write to some storage engine like Redis, and problem solved. But this still isn't completely solved. And this is something that most people just ignore. What happens if node 2 catches on fire here? So boom, node 2 is gone. Well, now the process responsible for cleaning up those users is gone. So user 2 is not going to be online forever in Redis, and that's not good. So at this point, you can come up with convoluted, maybe use a storage engine that has expiration times, but then you have to manage users online past that expiration, or have every other node monitor orphan users occasionally. But then if you have dozens of nodes, now you have a ton of nodes doing the same work. It becomes a mess. So we have 2 problems to solve with presence. One is we have local node concerns, where we have to account for unique presences for the same user. And the multi-node concerns are we have to handle node down events, and any user that was part of that node, we need to broadcast locally to our users saying, as far as we're aware, these users are gone. And then we also have to replicate data across a cluster. So our ideal solution is going to be something with no single source of truth, and that's going to give us no single point of failure. So we're going to have a more scalable system, a more fault-tolerant system, not relying on some central database like Redis, because if Redis goes down, the entire application goes down. Or if you're in a net split scenario, the unfortunate users on the other side of Redis are now worthless. So we can solve that with a CRDT and a heartbeat and gossip protocol. And that's what we're doing for Phoenix Presence. I'm not going to go into CRDTs too much. Alexander Sanj gave a great talk last year at ElixirConf, and he's the one writing our CRDT. If you're familiar with CRDTs, we've implemented an OR SWAT, which is an observe remove set without tombstones. Look it up, because I'm not going to try to explain it, because I can hardly comprehend it. So what CRDTs give us, though, is the key is we can have replication without remote synchronization. So we don't have to rely on some distributed consensus algorithm or some global lock. We can just replicate data across the cluster. If data arrives out of order or data arrives multiple times, it doesn't matter, because CRDTs, if you can fit your problem within the CRDT problem space, conflicts are mathematically impossible. So this is the key thing, that we can just replicate our data across the cluster. Conflicts eventually commute, or conflicts are impossible, so as long as all nodes eventually receive all messages, we'll have strong eventual consistency. And then we have a simple heartbeat protocol to actually replicate state right now. We're looking into gossip protocols. If you're familiar with Swim, it implements like an infection-style gossip protocol, but we're starting simple because heartbeats are very simple to implement and reason about. So heartbeats, in this case, we're piggybacking our CRDT deltas. So anytime our presence information, we have a join or leave, we just piggyback that on our heartbeat to other nodes. And then to detect node downs, you just say if node 2 misses some pre-configured heartbeat windows, we just declare them as down, and we clean up their state locally and broadcast to our users that are connected. So pretty simple to think about how heartbeat works. But once you get to like hundreds of nodes, it starts scaling poorly. But the first person that actually hits the limit of our heartbeat setup can sponsor Phoenix to implement a gossip protocol, because you're doing pretty well. But we can do some other neat things. So if you're familiar with vector clocks, or their version vectors in this case, vector clock is really just an integer value, and it lets us keep track of a node having state changes. So anytime a node has internal state changes, it bumps this integer value. And every heartbeat that gets sent across the cluster is going to include the vector clocks of all the nodes that we're aware of. So in this case, let's imagine node 1 has recovered from a net split, and it sees that node 3's vector clock went from 1 to 2. That means node 3 has updates for us that we haven't seen. But we also saw node 4's vector clock go from 2 to 3. That means node 4 has updates for us. So at this point, we could ask both nodes, like, hey, catch me up. I need those messages, those deltas that I missed. But then if we have dozens of nodes, we're going to have to send dozens of messages. So there's an easy way to optimize this. We can just say, like, aha, node 4 said that it saw node 3 at vector clock 2. So then we can guarantee that we can only ask node 4 to catch us up on the data we missed, and those vector clocks that node 4 has will contain node 3's updates. So we're able to optimize the net split recovery and new nodes coming up just by collapsing vector clocks and asking the minimal number of nodes for all the data that we need. So that's the internal implementation details. So at the end of the day, as an end user, like, you don't care, right? A lot of people just like to deploy Redis, and it's easy. So what this really accomplishes for me is, like, we're doing these really cutting-edge stuff underneath, but on the surface, the user land API is trivial, right? It's just going to make your life easier, not having to have this overhead of deploying Redis. But at the end of the day, this is all you have to write on the server. So after you join a channel, you can just say presence track. That's going to register your presence and start replicating that data on the cluster. And then to list the presences, you can say presence list, and that's going to keep track of unique presences even for the same user. And then on the client, we included a presence object on our JavaScript library that's almost like a CRDT on the client, where you can just say, anytime I get some initial list of users, I can just say presence sync state. That's going to handle the case where I reconnect. It's going to handle conflicts. And I can also call presence sync diff. I get this special presence diff event. Anytime data is replicated across the cluster, I'm going to get a diff of maybe hundreds of users that have joined and left, and I can handle that in a single place. And then to list the users, I can just call presence list, and I can pass optional callbacks to these to detect, is a user online for the first time, or are they online from a new device? Or has a user logged off entirely, or just logged off from a device? So you have metadata about devices users are connected to. And I'm going to show a quick demo of this because just to show you we've solved some of these trickier problems. So I have two tabs here. You probably can't read this, but port 4001 is node 1. Port 4002 is node 2. So we have two nodes running that are clustered together, and I can pass the name and the URL as the user. So pretty simple. We're showing a list of users, but if I want to open up a third tab, so I'm going to add a new user to node 2 named Evan node 2. And we can see almost immediately it was replicated to node 1 over here. So now I'm going to go back to the two original tabs, and I'm going to close Evan's tab. And we should see Evan immediately disappear from the right-hand side, and then within a second, he should disappear from the left as that's replicated. So gone and gone from the left-hand side. So we're handling the basic case of replication, users coming and going, but what about that tricky case that no one seems to solve? So if we have a node down event, I'm going to kill node 2, node 1 is running on top. It's going to stop heartbeating, it detects a node down from node 2, and if we go back to the browser, we can see that the node 2 user is gone. So we handled that case that almost no one handles or gets right. That's just taken care of for you. And the recovery case is pretty fun to watch as well. So I'm going to restart node 2, and we can see node 1 up top detects we got a node up, but if we wait a second, the coolest thing is they exchange information. So node 1 and 2 both send each other a transfer request saying like, hey, I haven't seen you before. You're a new version of this node. Give me any data that I've missed from you. And this is how node 2 was able to get updated information by asking node 1, like, hey, catch me up. And if we go back to our browser tabs, even the clients have built-in recovery. So now we can see our list of users are back and in sync. So the client is doing exponential back-off recovery, as well as the server's handling the net split and new nodes coming up and down. So that's presence. At the user land level, it's very simple, but there were tricky problems to solve, and I'm super excited about kind of where this goes in the future. I think people can implement service discovery on top of presence. It's not just applicable to chat lists. I think there are some really neat things we can build on top of this, and it's implemented in a way that allows you to kind of do some neat things on top outside of like a web browser. But the whole point of this is what I've learned throughout this process, especially optimizing PubSub, is like good platforms drive you towards optimal solutions. So when we started PubSub, we did a best effort solution, and with just minimal tweaks, by actually simplifying in the code, we were able to go from a best effort solution to a world-class solution. All because we trusted that like following these OTP principles was the secret sauce, right? And that's what we went into, drinking the Kool-Aid, and at the end of the day, it turned out that it came true. And I think it's a testament to the Erlang ecosystem, that we had this platform, we followed the tried and true tools in place, and it led to a world-class solution. And it also, it lived up to the hype as far as like our fast code doesn't have to equal dense code, right? I didn't have to suddenly take that PubSub system I wrote initially as like the happy path and then make it convoluted to make it fast. And on the flip side of that is I can write productive code and it doesn't have to be slow code. Like there's no dichotomy here where if I want to be productive, somehow this code is going to be slower. It's like, no, I can use OTP principles and the Erlang VM, and I get the best of both worlds. And ultimately, what good platforms do is they let us focus on what matters, and that's our application, right? I think at the end of the day, like you don't care if we're using CRDTs or Gossip or Heartbeat internally, but what you do care about is building your application. And if you don't have to worry about deploying extra infrastructure, or you don't have to worry about net splits and how you're going to recover or handle conflicts, if that can just be taken care of for you, that's going to let you focus on providing value to your customers or your business. And I think, what Phoenix is all about, what Elixir and Erlang are all about, is something that I stole from the Elm website. And as Elm says, writing road code should be easy. Now it is. And I think this is really what these platforms enable. They enable people to come in and write really world-class solutions, and it shouldn't be incredibly hard. It shouldn't be convoluted. And I think we've solved that on the server side, building on top of the great innovation that Erlang has. And I'm really excited to see what Elm has on the client side. And for that, I'll hand it off to Evan.
So I designed this programming language called Elm. How many of you are like familiar, like heard of this thing before? How many people have used this thing before? Okay. How many people have like built something for like pretty decent sized? Okay. So this project really got started because I was frustrated doing JavaScript and HTML stuff. Essentially, I wanted to put a logo in the middle of a box, and I couldn't, and I just was like, how can this work? And at the time, I was at a company where you'd expect things to be nice. I was working in technologies that were 20 years old, and I just was like, it needs to be not just horizontally centered, but also vertically centered. And it was just like, there are 6 solutions, they have different trade-offs, you need to choose carefully. I just was like, how is this reality? And another thing that came up is like eventually I decided that I didn't actually want it to be vertically. I didn't want it centered. I was like, that's not a good design, and did something else just to avoid the problem. And I had this sidebar that I then wanted to reuse on all the pages. And so I was like, oh, how do you reuse like visual components? And the answer is like, oh, you don't do that. That's JavaScript's not for that. So now you need to use a templating language on your server that's going to generate this HTML sidebar, and I just was like, how can it be like 2010, 2011? And the answer of how do you reuse this code is like, oh, we didn't think about that yet. Like that. So that was really how I got started with Elm. And I'd come from a background of typed functional programming and felt that we could take the lessons from that and apply it to this kind of problem that was very frustrating to me. So over the past couple of years, I've been developing this language. These days, I'm at a company called NoRed Inc., which is the biggest Elm user in the world. Not massive, but we have about 5 people who are full-time Elm programmers writing their whole front end in Elm. And there are a bunch of companies sort of in this range of like 3 to 5 engineers using Elm for stuff. And also, NoRed Inc. is hiring. So what's been interesting recently is I've been starting to meet Erlang people just in the course of running Elm meetups and doing Elm sort of stuff who, first of all, like that's not someone I expect to meet when I'm doing like more JavaScript focused stuff, but people show up at the meetups and be like, oh, like I really like get this. And we've seen this at NoRed Inc. as well. So like Erlang and Elixir folks are getting excited about Elm. Elm people are getting excited about Erlang and Elixir. And so our backend stuff at NoRed Inc. is in Ruby, and they're like, what's the next? How do we improve here? So you're starting to see these two communities come together. And so for the past, I'd say, couple months, I've been focusing on how can we make this really work really nicely together. And I was like, I'm going to demo how Phoenix channels and Elm are going to be amazing together. I didn't finish in time. So in like a month, it's going to be amazing. Right now, it's like, right now, it's just really good. So what I'd like to do is sort of show sort of the fundamentals of Elm, and sort of I'd like you to come out of this feeling like, oh, I think I know Elm. Like I think things are fine. So yeah, so I want to just start out showing sort of this core question that I started out with, which was I want to be able to reuse sort of parts of my UI. So in Elm, we have this HTML bindings. One second. Can people read the code okay?
Yes.
Okay. Okay. So hey, we made our first Elm program. So the idea is that we treat HTML as a value, just like numbers or strings. And once we have that sort of as a part of the language, you can start to build up quite cool stuff. So if we want to get fancier, we can have a div with no attributes, and then like multiple things. So like maybe, how are you? Oh. Someday I'll buy it. So yeah, so you can see now in typical HTML fashion, you put 2 things in and it's like, oh, it's going to lay out silly. But you can start to build these things up in a pretty pleasant way. And what's neat is these are just Elm values. So this is a list. Div is a function that takes 2 arguments. And so if you want to get a little bit fancier, you can say, I want an image where the source is this, and it's got no stuff in it. Let's see. Oh, fake out. Okay, so we can build up fancier things, right? So at this point, like we basically have a user profile, It's just CSS the rest of the way. So let's make this reusable. And so now our main can be a div, and its entries are Yogi, Steve, Alice, and their photos aren't correct in every case, but the idea is here, you can start to make these small reusable parts and build up full UIs. So this is nice, but it's not very interactive, right? Like this is probably not going to make your company a lot of money to have just like this static page that no one can interact with. So the crucial part of Elm is figuring out how can we start to interact with this in a way where we still keep the underlying principles of, I want to have a language that's typed. I want to have a language where everything's immutable. I want to have a language where all effects are managed, so you can't be doing arbitrary stuff. So Elm has this thing called startup, which sort of hides some of these details. So what we're going to do now is go from just having some visual stuff to having a counter where we can increment and decrement the number. Okay, so not the most exciting application, but sort of the fundamentals where once you can do this, you kind of can do whatever you need to do. Okay, so the core way you sort of set up an Elm program is first you start by modeling your problem. You then say how to view that model, and then you say how to update. Let's do it in a different order. You say how to update it, and then we'll say how to view it. So we want to make a counter. So to model the complexity and all the details, the essence of our counter application, we just need a number. So our model is going to be an integer, and we'll say initial model equals 0. So nothing crazy. And when you start to update things, you create a type that we can call action, and it can either be an increment action or a decrement action. These are the only two things that can happen in our application. We're going to represent that explicitly, and that actually gives us some cool stuff that we'll see in a little while. And so our update function is pretty easy. I take an action and a model, and in the case that it's an increment, I want my model to be higher. And in the case that it's a decrement, I want my model to be lower. Okay, so very straightforward. And finally, our view. We take our model. The address, just pretend that you understand that part. Part of this next release of Elm is to sort of get rid of some of these details that are truly non-essential. This is one of these details. So let's say we have a div. I have a button, and on click, I'm going to say increment, and it's going to have plus. Decrement, it's going to say minus. And then we'll have a div in here that says text to string model. Okay, so we're just saying, like, whatever is going on, this is what our application should look like. And finally, let's hook it up. So our main is now going to use start app. So you can, model equals initial model, view equals view, update equals update. So this is kind of like the boilerplate that will go in any Elm program just to like start things up. which is why it's called start app. You're starting your app. I try to go with like a literal names policy. So like if you want to use HTML in Elm, it's Elm HTML. If you want to like get a package from Elm, it's Elm package. Okay, so let's see if this works. I don't know. Oh, cool. Okay, so yeah, we can start to see the error messages stuff. So one of the things that I'm quite proud of is the quality of error messages. We'll come back to that in a bit, though. Okay, so we have our counter example. So I can increment and I can decrement. Now, what's cool to notice here is that when you set up your view, you just say, this is what it looks like when I show my model. And all the details of messing with the DOM, like poking around, that's taken care of. So sort of in the same way that, so when you're normally writing JavaScript, you have, here's how we make the initial version. And then things are going to change, and then you have to manually manage that. So you now have a two-phase process to do something. And I think there's an analogy here to sort of managing failure in that you say, here's how I'm going to start my system, and if it goes down, just like do it again. Don't try to like micromanage all those details yourself. This is kind of the essential pieces of Elm. Once you have this foundation, you can start building on it. So let's say our customers are really happy with the counter that we've created for them, and they say it's very accurate. It updates very quickly. We like the UI. It's very minimal. I think we could update the style to be like more flat and modern, but otherwise very pleased. But we want to be able to know what was the maximum number that anyone ever achieved. And so whenever you have this new requirement in your application, you always just start out by saying, what needs to be added to my model? So in this case, we still need to have the current value, which is an integer. But we want to keep track of the maximum, which is also an integer. So we update our model, and that sort of flows through and then we just like follow that through our application. So we can say current equals 0, maximum equals 0. Our update gets a little bit trickier. So now our model is a record. So we can say my model is, I want a new record where current is updated to model.current plus 1. And decrement, I want a new model where current is model.current minus 1. And yeah, let's keep the rest the same. So this is wrong, right? But so we can see everything going on. And we just need to add, okay, so in addition to when we increment, we need to check to see if we should update the maximum. So we can say maximum equals the max of model.maximum and this stuff. So we could make a variable so we're not repeating ourselves, but I won't get into that at the moment. Dun, dun, dun. What? Oh, it's ambiguous. Man. Okay. So now, as we move around, we keep track of the maximum. So this is what it looks like to add a feature. Just what does it mean to be this application? What is the essential data? How do I pipe that through? So another thing we might want to add is the ability to reset our counter. So in that case, we're explicitly modeling with the things that can happen. And we have a new scenario, which is reset. And in that case, we'll just say initial model. And we'll add a button for that. Okay, so there you go. So yeah, so at this point, you know how Elm works. Like, this is it. This is what you do. And we didn't show CSS, but it works the same. You can put a style here and do some stuff with it. And so we actually have sort of an architecture tutorial. So one route through reality that we can go is, we won't go this way, but so essentially this takes these basic building blocks and shows you how to nest them. So in the end, you kind of get a sort of, in the same way that Erlang says, oh, here's how you architect this so that your life doesn't suck. Elm has the same kind of thing, so we call it the Elm architecture. And we're starting to see this sort of in a bunch of JavaScript libraries, so React is sort of moving in this direction. So yeah, and so one other thing I wanted to show was our error messages. So oh geez. Can we see this at all? Yeah. Is this a little better? Okay. So one of the big complaints about typed functional languages is that the error messages suck. And so you'll be making something. So on the one hand, it's like, if people say if your program compiles, it will work. But getting to that is often frustrating enough that people are like, whatever, I'm going back to JavaScript. It will at least work, So sort of culturally, what sort of happened is the thing that people normally say is, well, you get used to these error messages at some point, and I didn't want that to be the answer. So I spent a good 2 months focusing on how can we make these really, really excellent. So as part of that, we made an error message catalog, which is whenever someone in the community finds an error message they're unsatisfied with, they report it, and we try to sort of coherently get better results. So right now, we're looking at a repo of programs that don't work. And the point is, if we can have them all in one place, we can make changes to the compiler and see that they all are improving. Like nothing is getting worse as we try to make improvements here. So this program I'm showing, is going to take a Boolean and turn it into the other one, and we gave it a number. Okay, so okay. So one of the first things to notice is that is that the way we display the code is actually literally what the person wrote in their source file. So if we want to be like maniacs, oh no, it trims, damn. Hold on, now we'll see it. No, wow. Okay, that's not what I expected. That still demonstrates, though, that you're seeing it actually how it was. So when it's a subregion, it'll cut to the particular expression. I'm surprised by this. So the point is, though, we give a very particular thing. So the argument to function not is causing a mismatch. It's expecting the argument to be a bool, but it's a number. That's just literally the problem. Explained for humans to read, where a way where you can look at this and it's literally what's in your code. So it's sort of optimized for a really pleasant debugging experience. So let's find a trickier one. Okay, this one's kind of nice. So in this case, we have a if. So if things are true, we're going to give a string, else we're going to give a float. And so again, we have this. The branches produce different types of values. The then branch is a string. The else branch is a float. We also have a hint system. So a lot of times you'll get an error message, and it'll just be like, hey, these things don't match. and you're like, okay, but I don't know this language, so like, what should they do? And so here we say, yeah, so they have to match, so whatever branch we take, we're going to end up with the same type, and things can proceed. And basically, whenever you do like weird stuff, the compiler is going to be there to help you out. So I think this one will be fun. So in this case, we have Alice and Bob, and they both have facts about each other. And like, you wrote them, and you're like, whatever. And you want to see if Alice and Bob are equal to each other. So L, make, type, sub, mismatch, record. OK. So Bob is causing a mismatch. It's expecting something where the position field and the y field of that is a float, but in fact, the position and the y is a string. And so when we have these type mismatches, we actually show the whole thing and sort of trim out any details you don't need and highlight the actual differences. So again, just like by virtue of thinking about how people's minds work, we can get you really quickly to know what's going wrong here. So like, let's say we fix this, but we call it Postion. Yeah, OK, this is, I think, my favorite error message. So if you just saw this alone, it'd be kind of confusing. It's like, I'm expecting the right argument to be position, but the right argument is, in fact, position. And like, the way brains work, you're just going to read it the same. You're just going to be like, oh. But so we actually find typos. And so we'll say, oh, did you mean one of these? So we can really easily suggest, like, here's how to fix your code. And so I think the end goal here is, the goal with them is how much can tooling really sort of recover from mistakes that in other languages just would kind of be a disaster, right? So like when you see people getting started with languages that don't have this kind of stuff, this might be the deal breaker, right? Like they're just looking at their program that like seems fine, right? There's nothing obviously wrong here. And if your error message is just like, no, you can't do that, and this is your first day with Elm, you might be, well, with JavaScript, I can do that, right? Like this language doesn't work. So this focus on error message, I think, has been really important to sort of helping Elm get traction in the front-end world, and also, also sort of breaking down this barrier of this like distrust of types. So we often don't talk about typed versus untyped. We talk about things like, hey, what if your error message is, instead of undefined is not a function? Or this would be some sort of undefined craziness eventually in JavaScript. You actually have like, hey, here's how you fix your code. And that's a more powerful message. Additionally, instead of saying types guarantee safety, we can say things like, if you use Elm, you don't get runtime errors. And like, if you're a JavaScript programmer, you're like, are you a liar? Like that can't be reality. And then the response is, I mean, you try it out and see. So you build this sort of like mystery, or not mystery, but like this like sort of challenge for people. And naturally, programmers want to prove you wrong when you make bold claims, and then they try it, and then they can't, and they're like, oh, this is pretty cool. I'm running out of time, but hopefully that sort of gave you sort of a basis in how Elm works, what it might look like to start using to write applications. One thing I didn't mention was how you start integrating. That's a little bit more complex and is the focus of what I'm doing right now. So the next release of Elm is really going to be about how can WebSockets not just be nice, but be maybe the best client-side WebSockets we've seen.
I didn't notice that it was different. Could you put an extra line that says, this is not the same word twice, they are spelled differently?
Even here?
Yeah, I can see it.
Yeah.
I'd say, this is not the same word, it's two different words and they're spelled differently.
Yeah.
That's what I want to see.
Yeah, that would be Yeah, that would be a nicer hint. But yeah, so I'll add this to the error message catalog and try to get this in the next release. But yeah, oh sure.
If you actually move the hint up towards the top, it would be much more intuitive. Maybe.
Yeah, there are lots of trade-offs along these lines. So, so thanks for taking a look. Hopefully this seems somewhat interesting. And just come talk to me afterwards if you have questions. Happy to talk about stuff. So thank you.